This problem gives us a head start by giving us the parametric formulas. All we need to do is identify the variables that need to be plugged in. So for instance, we have three of them here: v naught, theta, and h naught. Note that v naught is initial speed, which, as we can find out, initial speed of 150 feet per second can be identified very quickly. Furthermore, we have an angle, which is of course theta. So theta is equal to 22 degrees. And lastly, we have h naught, which is an initial height. And we see that the ball would leave Jones's hand at a height of 5.5 feet. Now that we have all of the variables that need to be plugged in, all of these constants here, we can just plug them in for part A. So x would equal 150 cosine 22 t. Y would equal negative 16 t squared plus 150 sine theta, which theta is 22, t plus, in this case, 5.5. Alright, now that we've answered part A, we've created parametric equations that model the position of the ball. We can answer part B, how long is the ball in the air. Now I might want to modify these equations slightly in order to answer the questions. That is, we could estimate the value of cosine 22 and sine 22 by plugging them into a calculator. That's up to you if you'd like to do that. I like to try to avoid estimating until the very end of a problem, and that's generally a good practice, so I won't be estimating for this part of the problem. Part B asks how long the ball is in the air, and in order to figure that out, we need to find out when does the ball start being in the air, and when does it stop. The starting being in the air is pretty easy. It's right when the ball leaves the hand of the pitcher, which is at t equals 0. When it ends is when it hits the ground. So in other words, when y equals 0. So we have an equation for y, thankfully. We can just set it equal to 0 in order to find the other t value. Negative 16 t squared plus 150 sine 22 t plus 5.5. Then, in order to solve this equation, you can use the quadratic formula, or if you have a calculator with you, you can use your polysolve on your calculator. That's what I'll be doing here, is using a calculator to solve this formula. Now this will actually give us two answers. The calculator will spit out two numbers here. It'll spit out a positive and a negative answer. Now we actually only care about the positive version because the negative number predicts that in the past the ball would have hit the ground if its trajectory would work in the past. But of course, before that 0-second mark, the ball was in the pitcher's hand, so it didn't have that trajectory. We can then say that we just use the positive version, which is roughly equal to 3.61 seconds. Since we go from 0 seconds to 3.61 seconds, that's a 3.16 second duration. So it is in the ball for 3.61 seconds. And that could be our answer for part B. Part C asks us to determine the horizontal distance the ball traveled, assuming it contacts nothing on the way to the ground. The horizontal distance the ball traveled, only travels while it's in the air. We're not assuming that it rolls when it hits the ground. And so we have to figure out where does it hit the ground. Well, we know when it hits the ground. That's actually the entirety of what we did for the last problem. So since we know when it hits the ground, we need to know where. Where's what horizontal distance? And luckily, we have an equation for that. That's x. So we can plug our t into x. We have 150 cosine of 22 times 3.61. And then we'll get our answer. And I get 502.07. Since our original measurements were in feet, and this measurement would also be in feet. Part D asks us for a maximum height. Now, when dealing with quadratics and asks for a maximum, we can compute that by finding the vertex. The vertex can be located at h, k, which then the h value is the when, and the k value is the maximum height itself. So first we can find the h, which luckily has a value, has a formula. It's negative b over 2a. Now remember, we're maximizing height, so I need the equation for height. And luckily, that's just y. B and a are just the coefficients to the second and first term, respectively. So the second term is negative 150 sine 22, and the first coefficient is negative 16 there. Again, we can plug this into a calculator to find 1.756. And recall that using this formula on this negative b over 2a on an equation, on a quadratic equation, finds the independent value. So here it's going to find t. So this is seconds. This is when the ball reaches its maximum height. The maximum height itself can be found by plugging the 1.567 back into the y equation. In other words, it would find k. So we have y is equal to negative 16 times 1.756 squared plus 150 sine 22 times 1.756 plus 5.5, which, when we plug that into a calculator, we find 54.8348. So I find roughly 54 point, let's say 835. And again, the measurement would be in feet. That answers part D. We found when the maximum ball reaches its maximum height and the maximum height itself. Part E is asking us to determine the horizontal and vertical positions of the ball 1 second after it is thrown. Luckily, that 1 second is a t value, and we want to know the horizontal and vertical positions. Luckily, that's just x and y, so we can just plug that 1 in. All this is asking for us to do is plug in 1 into our x and y equations. That is, x would equal 150 cosine 22 times t, which t here is going to be times 1. And for y, we have negative 16 times 1 squared plus, I believe it was 150 sine 22 times 1, and then plus 5.5. Both of these numbers can be plugged into calculators in order to find 139.078, and the other value is 45.691. Alright, and both of these measurements would be in feet.